All right, so here's another example. We've got a reaction between PCl5 and PCl3 and Cl2. We have some initial concentrations of PCl3 and PCl5. At equilibrium, we have an equilibrium concentration of Cl2. This is all done in a 1 liter flask. So since concentration is moles per liter, the number of moles is equal to the concentration here. Okay. We want to find the equilibrium concentrations of all species and then the value of K from this information. Now, you're going to do an ice table for this, but you're not going to have any variables because you know the equilibrium concentration of 1. You just have to take into account what happens, what that means in terms of the reaction. So copy this down and let's take a look at it. All right, so here's my ice table. Initial concentrations of the PCl5 and PCl3 are given. We know that they're going to change, right? PCl5 is going to go down by some value x. PCl3, it's 1 to 1, so that's going to go up by some value x, and Cl2 was 0, and it's going to go up by some value x. But we know what the sum, we know what the final answer for Cl2, the equilibrium concentration of Cl2 is given. 2.00 times 10 to the minus third is what its concentration was at equilibrium. Well, that's what x is. That's equal to x. So since I know the equilibrium concentration of one of my things, I therefore know what my variable x is. All I have to do is then subtract x from 8.70 times 10 to the minus third and add it to 0.298. And I get my final concentrations. Now to find K, I just plug it into my K expression. Concentration PCl3, concentration of Cl2 on top, divided by concentration of PCl5 at equilibrium. Those are the equilibrium concentrations. And I get 8.96 times 10 to the minus 2. So there's a situation where we didn't have to do any kind of weird algebra or use the quadratic formula because I knew what x was to start with. I just had to figure that out by putting it into the table. One of the things that can make your calculations a little bit difficult is the fact that sometimes you're going to, depending on the coefficients of a reaction, you're going to have some fairly large exponents. You might have something to the third or fourth power. That makes the algebra a bit of a bear. The good news is that we can use sometimes something called the approximation rule, which works if our value of K is very, very small. Then we can assume that the change, the value of x, is going to be really, really small, and it's not going to affect our initial concentrations very much at all. What that means is that we can then substitute or cancel out some of the part of the expression to make the algebra a little bit more simplified. So for example, if you look down here, let's say our value, and this is just taken from any old problem here. So for example, if you look at our problem here, this is just taken from any old equation, doesn't really matter. When we set up our K value, we have x times 2x squared over 1 minus 2x squared. Okay? If we assume that K is very, very, very small, we can say, well, okay, if K is very small, then the value of x is going to be very small. And if x is very small, then 1.0 minus 2 times something very small isn't going to change 1.0 very much. And so I can just essentially say that that's essentially equal to just 1. And so that just gives me 4x cubed over 1 instead of 4x cubed over this long quadratic expression. So it's an easy way to simplify. And I'll show you that in an example so that you can understand how that works. Okay, here's the example. Now, there are 3 problems here. I'm going to do the first one. You can try the other 2 on your own. Okay, so we have a K value for this reaction, NaCl going to NO and Cl2. And we have some initial concentrations to start with here. We're going to figure out the equilibrium concentrations for the mixtures that are given. And I'm going to do the first one for you, which is 2 moles of NaCl in a 2-liter flask. 2 moles in 2 liters. That means that the concentration of NaCl to start with is 1 molar, 1.0 molar. Okay, so that's what we're going to start with. Let's do the first one, and then you can just follow the model and do the other 2. Okay, here's our reaction. Here's our K value. We're going to set up an ice table, I, C, and then E for equilibrium concentrations. Initial change, equilibrium. Okay. According to the first mixture, it was 2 moles of NaCl in a 2-liter container. That gives me a concentration of 1.0 molar. There was no NO and no Cl2. Nothing has happened yet at the beginning. Okay. All right. Now, the coefficients of NaCl and NO are 2s. The coefficient of Cl2 is a 1. And that's going to figure into how I write my X's down here. Okay, NOCl is going to go down. The concentration is going to go down by some amount. Okay, but I'm going to use the coefficient here, and I'm going to say that it's going to go down by 2x. And the reason I'm going to do that is so that, because this is a 2 to 1 for chlorine, I'm going to say that for every 2 moles of NOCl that decrease, 1 mole of Cl2 will be produced. So it just makes it so I don't have to use fractions in here. Okay, so this is going to go down by 2x. The NO is going to go up by the same amount, 2x. Okay, and Cl2 is going to go up by only half of that, because it's 1 mole to 2 moles. Okay, so at equilibrium I have 1.0 minus 2x. I have 2x here, and I have x here. My K expression for this reaction is concentration Cl2, concentration NO squared over concentration NOCl squared. All right, so I plug in my values. I have x times 2x, which is squared, divided by 1.0 minus 2x minus 2x all squared, and that's equal to 1.6 times 10 to the minus fifth. Okay, my value of K is fairly small, 1.6 times 10 to the minus fifth. I'm going to then say that the value of x is going to be so small that subtracting 2x from 1 is not going to change 1.0 very much at all. Sig figs, right? So that means that I'm going to approximate. I'm going to make this the approximation. I'm going to say that the top isn't going to change because I don't have anything to subtract it from there. So that's just going to be 4x cubed on the top. And the bottom is now going to approximate to 1 minus nothing squared, or 1.0 squared. Okay? And that's equal to 1.6 times 10 to the minus fifth. My x value, therefore, comes out to be 0.016 molar. Okay? Now, all of 0.016 I can put in there and I can subtract, but what I want to do is I want to check to see if my approximation is valid. And here's the rule for checking my approximation. The value of x must be less than 5% of the value that I was subtracting it from. In other words, the initial concentration of NOCl. So 0.016 over 1.0 has to be less than 5% times 100, right? Has to be less than 5%. Well, this comes out to be 1.6%. 1.6% is less than 5%, and that means that my approximation is valid. So that means I can use it. Okay? If when you check it, it's greater than 5%, you have to go back and just do it out. You got to do the algebra. Okay? So my x value then is 0.016, which means I'm going to subtract 2 times 0.016 from 1.0, which means it's just going to be 1.0. 2 times 0.016 for NO, and 0.016 will be Cl2. So concentration of NOCl at equilibrium is 1.0 molar. Concentration of NO at equilibrium is twice 0.016, which is 0.032 molar. And concentration of Cl2 at equilibrium is equal to 0.016 molar. Those are my equilibrium concentrations for this example. Okay. Now, when you do the other examples, you're going to have a different I row. The change row is going to pretty much be the same, and your equilibrium row will change based on what your initial concentrations are. Try the approximation rule. For this example, approximation rule worked. It should work for the other ones because the value of K is pretty small. Okay, so give it a try, and if you have any problems, ask in class.